welcome to the last session under Unit 1, which is identification of aromatic compound by NMR spectroscopy. So, at the end of the session, you should be able to identify a compound as aromatic using proton NMR spectroscopy, identify a compound as aromatic using carbon-13 NMR spectroscopy, and locate the absorption signal of an aromatic proton in the NMR spectrum. Okay, so we know about NMR spectrum. We know there's the proton NMR and then the carbon-13 NMR. And first of all, we will look at proton NMR. Now, in NMR spectroscopy, what we are more concerned about is the chemical shift of either the proton or the carbon atom. So the proton in the NMR spectrum has a chemical shift peculiar to protons attached to aromatic rings. However, if the proton is attached to a different carbon atom which is not in the aromatic ring, then that proton has its specific chemical shift in the spectrum. So in proton NMR, the aromatic protons give an absorption signal in the range of 6 to 10 ppm. So that's where the chemical shift is. Now, for instance, if you take benzene, for example, only a single peak is found at 7.2 ppm chemical shift. Now, this is because all the protons are equivalent in benzene. And I'm sure we know of what equivalent carbons are. So this carbon is attached to one carbon, this proton is attached to one carbon, this carbon is equivalent to this carbon, equivalent to that carbon, all the hydrogens are equivalent. So we don't actually see 6 protons in the proton NMR spectrum. No, we only see one spectrum, one singlet or singlet peak as a range of 7.2 ppm. Now, how do we explain this in terms of electron delocalization? Now, it's important to know that the proton signal in NMR spectrum appears at low field strength, so the nuclei are deshielded compared to the normal alkenes. What it means is the protons in aromatic systems are completely different from the protons in alkene functional groups. And then I think we've already established the fact that the double bond in benzene is completely different from the double bond we see in alkene. So the protons in benzene, or the protons attached to the carbons in benzene, appear at low field strength. So the nuclei is more like deshielded, and all these signals are found at this chemical shift. However, protons in alkenes are found at this chemical shift in a range of 5.7 to 4.6 ppm. So any proton or any signal showing here tells us that the proton in this structure is not attached to an aromatic ring, although it may be attached to a double bond. That double bond may not necessarily be an aromatic carbon. But if we see the signal in this deshielded field around 7.27, then we can see that that proton is attached to a carbon in an aromatic ring. Now, when you look at carbon-13 NMR, carbon-13 NMR also wants to look at the actual carbons present in the molecule, and it has its chemical shift around 128.4 ppm. So whenever we have, and because all the carbons in this structure are equivalent, there's only one signal at this chemical shift. So only one signal for the proton, only one signal for the carbon. Even though there are 6 carbon, the proton carbon-13 NMR is not going to give us all the 6 proton signals. It's going to give us just one, simply because all these carbons in the ring are equivalent, and all of them are sp2 hybridized. However, there are cases where you might get an sp2 hybridized peak somewhere, but it may not be in the aromatic region. So be mindful of that.